All right, let's talk about something that is genuinely going to reshape our world: quantum computing. It promises to solve problems that our absolute best supercomputers today wouldn't be able to crack in a billion years. But to pull that off, it has to play by a totally different, and let's be honest, a much weirder set of roles. And this quote from the physicist John Preskill, it just hits the nail on the head. The quantum world is, well, it's just ridiculously complex. The amount of information it operates on is so huge that our normal computers, the ones in our phones and data centers, they just can't even begin to describe it. Think about it. To fully describe just 300 of these quantum bits, you'd need more classical bits than there are atoms in the entire known universe. No, seriously. So that leads to the big question, right? If this quantum realm is so unbelievably vast and complicated, how in the world are we supposed to build a machine that can actually control it and, compute with it? Well, it turns out the answer is to lean in and just embrace the weirdness. To really get what a quantum computer does, we have to start with its most basic building block. And the best way to do that is to start with something we're all familiar with, the good old classical bit. Okay, so the computer you're using right now, it runs on bits. You can think of them like simple light switches. They're either off, which is a 0, or they're on, a 1. That is it. A quantum bit, or qubit, is a completely different animal. It can be a 0, it can be a 1, or, and here's the crazy part, it can be both at the exact same time. It just exists in this kind of cloud of possibilities until the moment you look at it. And that gets us to our first piece of quantum weirdness: superposition. So, instead of that on-off light switch, picture a qubit more like a dimmer dial. It could be, say, 70% 1 and 30% 0 all at once, holding way more information than a boring old classical bit ever could. Okay, so a qubit can be in many states at once. That's cool and strange. But how is that actually useful? Let's see how this weird property actually lets you build a calculation. So here's the catch. The moment you try to measure or even just look at a qubit that's in superposition, poof, that whole cloud of possibilities just collapses. It's forced to pick a side. It becomes a definite 0 or a definite 1. Now, the probability of which one it'll pick is based on its state, like that 70-30 split, but the final result you get is fundamentally random. But this is where the magic happens. Because you can perform an operation on the qubit while it's still in superposition, you're basically doing that math on both the 0 and the 1 states in a single shot. And when you have a bunch of qubits linked together, you are exploring millions, even billions of possible outcomes all at the same time. It's a kind of massive parallelism that classical computers can only dream of. But, just exploring every possibility at once isn't quite enough. You still need a way to find the right answer in that gigantic sea of possibilities. And for that, we need our second piece of quantum magic: interference. So, if you remember the double slit experiment from physics class, you'll know that waves can add up and get stronger, or they can cancel each other out completely. Well, a quantum computation works kind of like that. Each possible path to an answer acts like its own little wave, and you can get these waves to interfere with each other. And here's the genius part. With a cleverly designed quantum algorithm, you can actually orchestrate this interference. The whole goal is to make the paths that lead to the correct answer reinforce each other. They get louder and stronger. And at the same time, you design it so that all the paths leading to the wrong answers crash into each other and cancel out. They basically get muted. And that's the whole trick. You set up this beautiful quantum dance where all the wrong answers just vanish into thin air, while the right answers get amplified. This hugely increases the probability that when you finally measure those qubits, the answer that pops out is the one you are actually looking for. This all sounds unbelievably powerful, doesn't it? And it absolutely is. But, like with any brand new technology that's on the bleeding edge, that incredible promise is matched by some pretty serious problems. First, let's just soak in the promise. The sheer scale is just mind-bending. A measly 300 perfect qubits can hold more possible states, that's 2 to the power of 300, than there are atoms in the entire visible universe. Let that sink in. This exponential power is exactly why quantum computers are such a potential game changer. But, okay, now for the reality check. Those answers we get are probabilistic, which means you have to run the same calculation over and over again to be sure you've got the right one. These quantum states are also ridiculously fragile. The slightest vibration or change in temperature, what we call decoherence, can mess everything up and cause errors. And on top of all that, these machines aren't going to replace your laptop. They're highly specialized tools for very specific problems. It all means we're currently in what's called the NISQ era. Our quantum computers are noisy, pretty small, and full of errors. So even with all those hurdles, the pace of progress has been just breathtaking. We've gone from what was basically a wild idea in a physicist's head to actual working hardware in just a couple of decades. And that pace is only getting faster. The idea really got going with Richard Feynman back in the 80s. Then, in '94, Peter Shor's algorithm gave it a killer app, the potential to break almost all modern encryption. Fast forward to 2019, and we get Google claiming quantum supremacy, where their machine did something no classical computer could. And now, it seems like records for the number and quality of qubits are being smashed every single year. And this is why we should all be paying attention. We're talking about the ability to design brand new life-saving drugs by perfectly simulating molecules, or creating new materials we can't even imagine yet. We could develop super efficient fertilizers to feed the world. And yes, there's the big one, breaking the encryption that protects our entire digital life. It could literally help us unlock the secrets of the universe itself. You know, Richard Feynman's original vision was to build a computer that operates using the same rules as nature itself, a computer that literally speaks the language of quantum mechanics. And we are right on the verge of actually doing that. The progress is real, the challenges are huge, but the potential discoveries are completely unknown. And that leaves us with a pretty incredible thought, right? What are we going to find out when we can finally have that conversation?